I've got here is evidence for advanced geodetic knowledge in archaic times. What is geodesy or geodetic knowledge? Geodesy is the determination of the size and the shape of the earth. Early in the 19th century, such knowledge was acquired by extensive land surveying and triangulating over large tracts of the Earth's surface. Since the 1970s, orbital satellites have provided the most accurate picture of the Earth's exact size and mass distribution. Any advanced comprehension of the larger picture of our planet as a suitable abode for the evolution of higher life requires knowledge of its size and shape. The total mass, of course, determines g, the gravitational constant. The equatorial bulge is an integral component of the forces acting to impose rotation and orbital stability on Earth as it wheels about the sun. The relevance of these two basic factors to the evolution of life cannot be underestimated. Ancient master builders understood Earth's fundamental geodetic parameters on a level not equaled until the advent of modern satellite surveys. How do we know that? Well, probably the most salient means we have of knowing that is the Great Pyramid of Cheops itself. And there's been lots and lots of speculation about what the form or what the function of the Great Pyramid was. Some of it to me is pretty out there. Some of it I think is pretty abstract and speculative. What I've always thought does make the most sense and has the greatest credibility is the pyramid is essentially a model of the Earth, the northern hemisphere, and I'll show you how here. The thing you have to understand when you're looking at the measurement of the Earth in terms of its size and shape is that we have lines. Everybody knows latitude and longitude. Latitude is measured north and south of the equator. Longitude is the measure around this way. Parallels are lines that run parallel to the equator. And traveling along one of the parallels, we would be displacing ourselves longitudinally. But parallels actually measure, you can see this parallel here, this is probably the Arctic Circle. It looks to me like about 66.5 degrees north. So it is parallel to the equator, right? So depending on what parallel you are, every line of latitude, north and south, has a corresponding parallel. And you know that from the equator to the North Pole is going to be 90 degrees, and likewise from the equator to the South Pole is going to be 90 degrees of arc. Then in turn we have meridian lines, which are lines that run north-south, but actually measure distances east and west. So that if you traveled from one meridian to the next, to another meridian, you would have traveled from east to west. Every point on the surface of the Earth has a local meridian. We have a local meridian here, and it's basically the way you would find it is if you walked out here. I believe this is generally south, isn't it, this way? So if we went out here and we looked exactly south and exactly north, and then the zenith overhead, the point 90 degrees up from a flat horizon, and we struck an arc from the south point through the zenith point to the North Pole, that arc would be our local meridian. And as the Earth turns under that local meridian, we measure all astronomical motion relative to our point on the surface of the Earth with respect to that local meridian. Now, you'll notice that as you go through the parallels form virtually perfect circles. The meridian lines, on the other hand, are not circles because of the flattening of the Earth. Because of the expansion of the equator, if you draw a line around it this way, and cut the Earth this way, it is not going to be a circle. If you cut it this way, it will be a circle. Okay, that creates very subtle differences in geometry. When you're measuring a meridian line north to south, what happens is that as you travel north away from the equator, if you are going on a perfect sphere, then each degree of latitude north would have the same distance. But it's not a perfect sphere, it's flattened. So as you're moving towards the North Pole, the Earth is actually flattening out. The Earth's radius is shrinking. So it's flattening out. What that means is that to traverse a degree of arc, you have to travel further as you get away from the equator towards the North Pole. Okay, I'm explaining this because you've got to understand this to see how the ancients actually understood, how they demonstrated to us that they understood the size and shape of the Earth with a high degree of accuracy. So again, parallels are going to be in circles, and you're going to notice that the biggest circle is going to be the equatorial circle, and as you travel towards the poles, those circles get smaller in size. So therefore, if you took the meridian lines, which would be the dotted lines, the distance between, say, 1 degree of meridians at the equator is going to be greater than that distance between the same two meridians, say, at our latitude here in Atlanta, which is about 34 degrees north, or further north. As you travel further north, those meridian lines converge until you would get to the North Pole, and then they meet each other and have zero distance between them. Okay, this is taken out of the Smithsonian meteorological tables, and what we're looking at here, without belaboring this, is you'll notice latitude 0 degrees, and you go through up to 90 degrees. And what this is showing is if we look into statute miles right there, this says length of 1 degree of the meridian. So this is the line from equator up to the North Pole. Well, if you look at the first number, which, let's see if we can zoom in a little here, you'll notice that at 0, when you leave the equator and go to the 1st degree north latitude, you've gone 68.703 miles. But if you look down here at the very last one, when you traverse that last degree from 89 and you finally get to the North Pole, you've traveled 69.4 miles. So those degrees have stretched out. Okay, now this is important to understand how the ancients were able to demonstrate to future generations that they understood the size and the shape of the Earth. And then we have length of 1 degree of the parallel. If you notice right there, I don't know if you can read it from out there, but that says 69.172 miles. So think of a circle going around the Earth's equator. You've traveled 1 degree, 1/360 of that distance around. You've gone 69.172 miles. Let's go halfway up from equator to North Pole, which would be 45 degrees, and you see right there, you've gone 49 miles. Then when you get up to the pole itself, when you're 1 degree away from the North Pole, you only have to go 1.2 miles because those meridian lines have converged. So now, the thing to grasp here is that if we're measuring the size and the shape of the Earth, that's going to vary depending on where on the Earth we're making those measurements. This is important because what we discover is that the ancient peoples knew this and incorporated it into their architecture so that they would derive units of measurement that were ultimately based upon the size and shape of the Earth where the structure was being built. Now let's take the most prominent one. Before we get to that, this is geodetic data, and you'll notice here we've got going back to 1830, which was the first attempt in modern times to determine the size and shape of the Earth. And let's go, since that's meters, let's go to something we'll recognize, miles. We're talking about the radius here, and you'll notice as you're coming down through here, we get to these last two, World Grid System 72 and Geodetic Reference System 80 are the two that were determined by satellite measurements. And you'll notice that as we come through here, we've got a polar radius in miles and an equatorial radius in miles. And then we have the difference in the two radii right here. And we assume that as we've come through, we're progressively getting better and better at measuring the size and shape of the Earth. And finally, with satellite measurements, we're getting down here, and we've determined that the polar radius, for example, 3,949.8934, 3,949.8948. What does that translate into? Well, let's see. In terms of feet, that's a difference of, 250 feet roughly between, between these two measurements. In other words, between the first satellite measurement in 72 and the second one in 1980, the difference was about 250 feet, say.